The wait is over. Let's move into infrared light.
Okay.
Give us the 101, what it is and why it's important.
We have known for a long time that there are seasonal aspects of death. We see much more deaths in the summertime, or sorry, in the wintertime than we do in the summertime. There's a number of data that came out of COVID that showed that even in the wintertime, the sun has benefits. So for a while, it sort of burned within me to look for the other aspects of sunlight that had nothing to do with vitamin D. So sure enough, an area of study called photobiomodulation was looking into light therapy for things. And this research has been going on for decades, but it's really picked up in the last few years. And what they have basically shown is that infrared light, which is light that has a longer wavelength than visible light, cannot be seen. You can feel it as heat, but it's not heat by itself. It actually is electromagnetic radiation. The majority of the photons from the sun are actually in the infrared spectrum. That this type of light, as opposed to ultraviolet light, is very easily able to penetrate not only through the atmosphere, but also your clothes. In fact, they've done research for some types of clothing. It takes about 10 to 13 layers of clothing to fully stop this type of light. So it can go right through your clothes without a problem. It can go right through your skin and actually come out the other side. Obviously not as strong because much of it gets absorbed in the body. There's a paper that I would highly recommend reading, two papers. One of them is called Melatonin, the Optics of the Human Body. That's by Russell Ryder and Scott Zimmerman. And another paper that was put out last year by Glenn Jeffrey and Robert Fosbury, who looked at a similar situation and was published in Nature Scientific Reports looking at longer, the title of that is Longer Wavelengths. And it talks about how longer wavelengths pass through the human body and actually can have systemic effects on a particular part of the cell. So let's back up here again. The sun. The sun has something called a photosphere around it. It's like an atmosphere, and it selectively allows infrared photons to come through easier, more easily. So that means that a sun that is the size and the temperature that it's at, specifically in our solar system, our sun is designed in a way that allows more infrared photons than would normally be expected. Okay, and that's really interesting. That radiation comes 93 million miles and comes to our Earth's atmosphere. And there are transparency windows in our atmosphere that allow certain types of light in much better than others. And that's because of the molecules that are in our atmosphere. You've got nitrogen, you've got oxygen, and that wiggling of those bonds absorb specific wavelengths of infrared light. Well, there are these windows of transparency that astrophysicists are well aware of, because if they want to see through our atmosphere, if they have an observatory high up on a mountain, they've got to look through a window of wavelengths through there so that there isn't any kind of interference with the atmosphere. Well, as it turns out, there's a number of windows in the infrared spectrum that allows this sunlight through their photosphere, and it penetrates easily through our own atmosphere. And it's this very precisely this type of light, this infrared light, that can go into our skin and can get down to a fair enough distance that it actually can have effectual changes. Where? At the mitochondria. Now, let's put that aside. If we were to look at many of the chronic diseases that we see going on in the United States, whether it's diabetes, obesity, congestive heart failure, dementia, COVID, long COVID, cancer, inflammation in general, at the epicenter of many of these chronic diseases is the mitochondria. In fact, the central theory of aging, Jesse, is this idea that as we get older, the energy output from our mitochondria, our batteries of our cells, start to drop off incrementally. In fact, some studies show up to 60 to 70% of the energy output in our mitochondria drops after the age of 40, after a number of years. So what we're seeing here is that there is a type of light, precisely this type of light that comes from the sun more than we should expect. We have an atmosphere that is perfectly set up to allow this very type of radiation through the atmosphere very easily. And we have our bodies in a way that allows this light to come in and interact at the mitochondrial level to increase, to improve, to enhance the amount of ATP and energy production in those mitochondria in just about all of the cells in the body that have mitochondria. And what we're seeing is not only changes epidemiologically, longevity, people who are out in the sunlight longer, but that has confounders with exercise. We are now seeing randomized, placebo-controlled sham studies that show that precisely this type of light from the sun in the infrared spectrum is reducing the length of stay of COVID patients in the hospital, is reducing the amount of glucose in the blood in patients who are healthy and are given a glucose tolerance test, are reducing the length of stay in ICUs by 30%, and they're coming out more actually stronger and less need of physical therapy. And the list goes on and on, the number of randomized controlled trials that show that sunlight, and specifically infrared light, is having this effect at the mitochondrial level in humans that are healthy and humans that have diabetes and chronic disease.
Okay, that's a great overview. As you're sharing that, it gets me thinking about infrared saunas.
Yes.
Is there any connection there between what's going on with a far infrared sauna and this light?
Yes, this brings up a very interesting point that we need to make sure that everyone's very clear about. The type of light, of infrared light that we're getting from the sun is multiple wavelengths over a large period. So we're talking 760 nanometers all the way up to 1200 or even beyond, even into long wavelength. Okay. The same thing from an incandescent light bulb. We're getting infrared light from about 760 way out in an incandescent light bulb. That's different fundamentally than us going into a infrared sauna or having a laser focused on us, because that's monochromatic light. That's infrared light at one particular wavelength. Do you understand what I'm saying?
I do.
Yeah, so these are very different things. Now, in both of these situations, we are seeing improvements in health outcomes. I don't want to come across as saying that one does all of the heavy lifting and the other one does nothing, because we have data in both groups that shows that a broad infrared light exposure does benefits, and monochromatic laser, one particular wavelength, also has benefits. However, what I am trying to say is that we are noticing that the benefits are more pronounced in the broader sense when a broad source of infrared light is going into the patient, as opposed to just one. And again, the data that I cite for that is Glenn Jeffrey's work. He's done work in the eye, which has the highest concentration of mitochondria in the retina. And again, the endpoint there was how well are the mitochondria in the cones producing energy to allow the patient, the subject, to differentiate between two color groups. When he used monochromatic light, he got about 15 to maybe 15% improvement, and not in every single cone. When he used an incandescent light bulb, every single type of color blindness improved. And it was not just 15%, it was north of 20%, 25%. So when you ask the question to me, what do I think about infrared saunas? I would say that the infrared sauna is a way of delivering infrared light, like we see in many of these studies where there is benefits. What I don't know is whether or not infrared saunas are superior to somebody just making more time outside in the sun.
Okay, good answer. Important we went there.
Yeah.
We'll put the sauna aside for now, at least then. We know now this infrared light can go through the clothes. It goes right through the body. You've highlighted a couple times now mitochondria. Let's take it to the mitochondria and explain what happens when this light interacts with them.
Well, this is really where it's coming down to. So there is some work that seems to indicate that there's a couple of electron transport proteins in the mitochondria that can respond and upregulate their use when they have infrared light shone on them. Let me just back up here for those that are not biochemists or chemists or people who don't understand how this works. I want you to picture the three different types of food that we consume: fats, proteins, carbohydrates. All of them are broken down into a final common molecule called acetyl-CoA. Okay, acetyl-CoA is a 2-carbon molecule that goes into it's in the matrix of the mitochondria, and it undergoes something called Krebs cycle. And what we're trying to do here is we're trying to extract high energy electrons off of this molecule so we can run the body. Okay, so again, whether you eat fats, proteins, or carbohydrates, all of that gets broken down into a molecule called acetyl-CoA or acetyl-CoA that has high energy electrons. Now, it goes in the matrix of the mitochondria. We're extracting these high energy electrons in the form of NADH and FADH2, if you want to be technical about it. These molecules, these NADH and FADH2, go to the electron transport chain. Okay, now what I want you to picture is I want you to picture the Colorado River. Okay, it starts off in Colorado and it goes through the western United States. And as it drops down, as it's on its route toward the sea, which is in Baja California, it will reach these lakes. And we've built in the United States these massive dams that basically collect the water and run turbines as we let it go down below. I think the analogy would be the well and locks there in Niagara Falls, right? So you've got Lake Erie, which dumps into Lake Ontario, and it goes through the well and locks and it goes down. But you also have a big hydroelectric, probably one of the first and biggest hydroelectric power plants in the world was built right there in Niagara, where water at 200 feet above Lake Ontario is directed and is turning turbines and generating electricity. So I want you to imagine these high energy electrons that are at a high level, and what the mitochondria is doing is it's allowing these electrons to transfer down the energy gradient. And as it's doing that, instead of turning turbines, what it's doing is it's pumping protons out into this reservoir around the mitochondria. Okay, so as you're eating food and it's being broken down and you're getting high energy electrons from the food, what the mitochondria is essentially doing is it's taking all of that, all the diverse foods that you eat, and it's saying, the final common pathway of all of this is going to be pushing protons into this reservoir on the outside of this mitochondria. Okay, because later what happens is these protons start to come back in through a pump, and this pump then creates ATP, and that's how you get energy. Okay, but let's focus on how they're pumping these protons out. As these electrons are going down the chain, as we're going down the Colorado River, as we're hitting, the different dams, Hoover Dam, and etc., all the way down to finally it drains out into the Gulf of Mexico. As this water is going down its gradient, instead of turning turbines, what we're doing is we're exchanging electrons. We're moving electrons down to pump protons through. Okay, here's where I believe we are now coming around to this thinking, and expect a paper on this coming up shortly to talk about the details. When water goes down its gradient, there's like a waterfall, okay? That's an electron transfer. If you want to talk about it biochemically, imagine a protein, and you're transferring electron from one area to another area, okay? When there's actually equations that you can figure out that'll show you what the change in energy is when you do that. And if those of you who are following and are biochemists, that's a negative delta G, which means it's a spontaneous reaction. Here's the issue though. Okay, here's the issue is when that electron goes from one area to the other, you can imagine now that the area that it left is now positively charged, and the area that it's going to is now negatively charged, correct?
Yes.
Okay. When that happens, because this is happening in water, and water is polar, there's going to be a change in the orientation of those water molecules, right? The water molecules that were over here before that were around the neutral protein are now going to be flipped around in a way because they have to buffer this positive charge. Does that make sense?
Yeah.
And similarly, the opposite for the negative charge. So in other words, there's an energy of reorganization that occurs. So that's not captured in the equation of the free energy. There is a barrier to that electron moving there, and that barrier is not just the free energy. There's an activation energy that occurs, and there's a reorganization energy. This gets into quantum mechanics. It gets into Marcus energy. Rudolf Marcus, who's actually still alive, he's 102 years old, living in Pasadena. He won the Nobel Prize in Chemistry in 1992 for his work in 1988 on exactly what I'm talking about here. And what he showed was that basically there's a reorganization energy that occurs when electrons go from here to here. It's not just the change in the electron state, it's the change in the actual shape of the protein, it's the change in the solvents around the protein, and that is a barrier to those electrons moving. So here's what I believe infrared light does. I believe that infrared light in many different wavelengths, okay, it changes it makes it easier for the water to restructure itself in a way because it's introducing low energy vibrational energy. So it's basically greasing the skids to allow this conformation change to happen more frequently, to allow it to happen more easily, and to allow the restructuring of the solvents to allow that electron to move more easily. So when you have that type of energy entering into all of your cells in the sunlight, and you have that ability to restructure the solvents, quote unquote, the reorganization energy, which is labeled lambda when you're talking about Marcus theory. The electrons, instead of having to go over activation energies to go down their concentration gradient and to go out, instead of that happening more slowly, now it's almost like a slide. Okay, the electrons can go down the electron transport chain much more easily. You have a much better pushing out of those protons into the inner membrane space. And of course, because of that, those protons are going to come back into the matrix and you're going to make a lot more ATP. And that's exactly what we are seeing in these experiments, Jesse. In Glenn Jeffrey's work, he gave normal subjects glucose and he had them drink this glucose. And he was able to measure in those that were not exposed to long wavelength light, the glucose spike went up a certain amount. And in those people who he gave this long wavelength energy to, which presumably was improving the organization energy, was allowing these electrons to fall faster, was pumping out more protons, there was more energy being produced at this time. And there was a over 20% reduction in the spike of glucose when these subjects to the glucose tolerance test. Now, he believes that this was because of mitochondrial metabolism, because in those subjects, there was not only a reduction in glucose, but there was an increase in the production of exhaled carbon dioxide, which we know is a product of mitochondrial aerobic metabolism.
Fascinating stuff. Wow, a lot we can get into here.
Yeah.
Where my mind goes initially, what does dosage look like for somebody that wants to see this benefit? Is it getting a daily exposure, or is it getting multiple exposures a day? And then also talk about different times of the day and then how much of this IR light is available.
What's really interesting about this is that Glenn Jeffrey has looked at bees, he's looked at insects, he's looked at humans, and he tells me, he's like, look, Roger, it's the same every time. It's like a switch. You get about 15 to 20 minutes of this infrared light, and that's enough to get the system going. And further stimulation really has diminishing marginal utility. So he's done these experiments, as I mentioned, in various different species. When we look at the randomized controlled trial data, when we look at the Brazilian study in COVID that was done in 2023, when we look at the MICU, SICU study that used infrared light in Brazil in 60 patients that was just published last year, how long did they give them infrared light to get the effect that they saw, which was dramatic? 15 minutes a day. 15 minutes a day. And we're not talking about a large amount of light. You know, a lot of us will believe that if a little is good, a lot is better, right? So if we were to look at the amount of infrared light in total that's coming from the sun and hitting us after it gets through to the atmosphere, you know, at the surface of the Earth, you're talking about 100 milliwatts per square centimeter. Okay? The energy that was given in these randomized controlled trials that showed tremendous benefit was 2.9 milliwatts per square centimeter. Not very high. You don't need a lot to get the benefits. And this is the reason why people are saying, you know, when we decry the fact that incandescent bulbs, say, why do we need to go to incandescent bulbs? You need to go outside. Incandescent bulbs only give a fraction of the energy that's coming from the sun. Guess what? You only need a fraction of the energy. We're finding out that the amount of infrared light that is necessary is actually diminishingly small. 2.9 milliwatts was the energy that was used in the Brazilian study that showed that these patients with COVID left the hospital 4 days faster. 12 days in the control group, 8 days in the intervention group. And that intervention group, by the way, started off sicker than the control group. Fascinating. Look, Tamiflu was FDA approved because it reduced flu symptoms for 24 hours. It stopped flu symptoms 24 hours earlier than the control group. We're talking about an intervention here that reduces 4 days off of hospitalization, 2.9 milliwatts per square centimeter. It's incredible. And the thing that I'm thinking about is that we're spending so much time inside. We have windows that on purpose block infrared light because we don't want to increase our cooling costs. We have replaced all of the lights in our homes with LED bulbs because we want to reduce energy costs. Essentially, what Bob Fosbury calls this is the scurvy of the 21st century. 300 years ago, British sailors needed food on their ships. And the way that they preserved the food, unfortunately, leached out all of the vitamin C out of their food. And so there was this issue with scurvy on British sailing ships because they were living in an environment that was perfectly designed to get the results that it did. And I know this sounds like wishful thinking, like it sounds like it's almost woo-woo, right? Here I'm saying that you just need to get outside in the sun, but yet what do we see on those British ships? Drink this ration of lime juice and your gums will stop bleeding. Your sailors, your colleagues will stop dying. It's that simple. I also believe that we have created for ourselves an environment that is completely bereft of precisely the same wavelength of light that the sun is actually giving us the majority of. And it is also very beneficial for just about every single cell in our body.
Good news in all this. The infrared light, as we've talked about, does penetrate clothing. You gave that example before of that, say, business person in Toronto not going outside all day. But we're only talking about like 15 minutes here being outside per day, and you can be clothed. So it seems like to me, for most people, they would almost have to try not to get that, even in the winter. If you're shoveling your driveway, if you're walking your kids to the bus, to me, it seems like most people should already be hitting this metric.
Yeah, so you're living in Ontario and you're saying, you know, Dr. Schwell, you live in sunny Southern California. Easy for you to say. First of all, I grew up in Toronto, so I know exactly what you're talking about. Here's the good news. The good news is that you don't need a lot of infrared light. Look, what is everyone concerned about in Toronto when you have a lot of snow, and you get a few days of sunlight, and some of that snow melts, and then it freezes at night because it's really cold. What is everyone concerned about the next day?
The roads.
Exactly. We're concerned about black ice. Why are you concerned about black ice? Let me prove it to you. It's the infrared light from the sun, even when the sun is low enough in the sky, that's actually melting the snow. Okay? The snow is highly absorbent of infrared light. So when that infrared light comes and hits the snow, it starts to melt. And at night, it refreezes. Do me a favor. You've got plenty of snow to try this out on. When you see the sun out today, hitting the snow in Toronto, you will start to see that it's dripping. It's dripping. And note the temperature. Okay, the temperature may be above freezing, it may be below freezing. It really doesn't matter. It's the warmth of that infrared light that is penetrating the atmosphere, even in Toronto, and it is melting the snow. Notice the moment the sun goes down and sets, even though the temperature has not changed, the snow will stop melting immediately. And you will no longer see any more drips. It stops. And that is because the thing that is melting the snow is the infrared light that we're talking about now. It is precisely the very same light that is available even in the dead of winter when the sun comes up, even in Toronto.
Since you made it to the end of this clip, I know you're going to love the full episode. Click here to watch. I'll see you over there.
We're spending so much time inside. We have windows that block infrared light because we don't want to increase our cooling costs. We have replaced all of the lights in our homes with LED bulbs. What Bob Fosbury calls this is the scurvy of the 21st century.